Hi. So let's now talk about geothermal energy. So you see the map of the USA, and this is the temperature very close to the surface, and you will see that we are really lucky. We have a lot of high temperature very close to the surface, and that's the key, that you don't really have to go deep inside in order to reach those temperatures. So of course, why the ground is warm? Because we are living on a molten core underneath, and so if you go deep enough, you will get very high temperature. But that costs a lot of dollars to go very deep. It's not as expensive as before because of all the technology that the oil and gas industry has developed. Then it's applicable over here, but still the key is you get very hot very close to the surface. Alright, and what's even why the reason why we are even more lucky in the US is because of the hydrothermal sites. So the hydrothermal sites is a places where you have hot temperature and also you have water trapped near that hot surface or heat source, and as a result the water become either hot water, which is good enough by itself, or even better, it become steam. And so all you need now, you have a steam. What do we do if we have steam as mechanical engineer? Send them to a turbine and get mechanical work out of it, right? So when you have a hydrothermal system, a hydrothermal site, that's perfect to actually extract that energy and turn it into mechanical power in our turbines. So you will see how this is actually already been done in the USA and all over the world. All right. So where all over the world, you will notice this is the area of uh, geothermal region, hottest geothermal region, and they basically unfortunately they also are the places where there are most active earthquake sites as well. Right. So that's the reason why it gets really hot. And so a place like this is Iceland. Here is a picture, and you can see the people are swimming in their basically hot tub over here with all the hot water coming out, and you can see a power plant sitting at the background. And so Iceland is a country where all the energy is coming from renewable energy, basically geothermal and hydraulic power. So they are not really paying for any natural gas or hardly anything, right? Most of the power is coming from geothermal, 26% geothermal and 73% are hydraulic. So they are basically living for free over there. So the the best places is where again you have hot surface very close to the or hot source very close to the surface, so you don't have to dig very deep, and water. And that's when you basically have uh, geysers or just basically steam. You can extract the steam and send it to a turbine, like for example Yellowstone National Park. And so here is the first mode of tapping into just geothermal energy. It's called hydrothermal, and again, as I said, water, very hot core, very close by. And this water, where did this water come from? Well, rain year after year, and then it's going through all the ground until it get trapped against basically that hard surface, and it's basically stuck over there. So either it make itself find its way out, right? That's what you would see in Yellowstone National Park, or you will dig for it, right? You will dig for it, and you don't have to go that deep, and you get your steam out. So now once that steam out come, you are ready to uh, turn this into a Rankine cycle, right? So here is a turbine, here is a condenser, and after the water condense, you send it back into the ground. And we talked about this in the ocean thermal energy. Why do we have to condense? We just extracted all the energy into the turbine to the generator. Why do we have to spend the money on building a condenser, and that condenser is being cooled by a cooling tower? The reason why we are doing this is when you expand in the turbine, the pressure drop, and the more you want it to drop, right? You want that turbine to work between big pressure difference so that you have big delta H, right? So that the work actual is big H minus very small h. And so the lower you can get, you want this to go as low as you can, right? And you send it as low as what? As the temperature of the condenser is allowing you to be. And the temperature of the condenser, how low it can get, it's the cooling tower that is cooling that condenser. And that cooling tower, how cold it can get, it's the air that's cooling the cooling tower, right? So you are basically stuck with the cold reservoir you are sending the Q rejected to. Okay, and once it become liquid, then that liquid is ready to be pumped into the ground, right? You increase his pressure and then you can send him back in, and he go back into the reservoir where you pull the thing in to be heated and you extract it over and over again. And if you are wondering, well, why do I have to send it deep inside? Don't I just I can just put it in a lake or something that's not really bad water. But this site will run out of water, so there is this water is, so the geothermal energy is renewable energy, right? It's the ground will stay, the earth's core will stay as hot as far as we are concerned. But that water will not. That water, you will run out of that water. You wanna keep sending that water so that you don't deplete your resource. But also the part about, will it really stay hot forever? Yes, the core will stay hot forever, but that site to get that hot, it takes, there is time scale. There is a little bit of time that needed to heat this to the right temperature so that you will generate the steam. But the good news is, by the time you run out of heat in that site, the turbine, the condenser, all those equipment will already be ready for decommissioning, right? They will not survive. The turbine and the boiler, or the turbine and the condenser and the generator, they will not live forever. And so by the time this is ready to retire, you will also be about to reduce the heat source over here in that water. And so they would say, well, then don't build a new turbine and a new power plant over here. Well, move to the a little bit far so that you will tap into another place where it's already hot. All right. So now the water or the steam that will come over here will determine if it's water dominated, you need flashing. If it's steam dominated, you just need kind of a separator to take any particles out, and it's ready for the turbine. So you will see both of them. So that's why he's talking about vapor dominated or liquid dominated. You know, on the TS diagram, am I extracting my water on the saturated liquid side or on the other side on the vapor saturated side? Is it water, or basically am I getting HF or am I getting HG, right? So this is hydrothermal, getting very hot water or very hot steam ready for the turbine. The geopressurized mode is basically you have a hot underground aquifer, but the water there is not really safe for the turbine. Why? It has high salinity, a lot of salt in it, and so we would call this brine. And so that brine, you know, you are not gonna let this go into your power plant because he will basically eat the power plant alive, right? Because of all the corrosion. So but it's really hot, you know, the temperature is really high, and you're like, look at all those joules, I cannot throw them away. So what should we do? We do the closed cycle, the same one that we did for the ocean. Remember the closed OTEC cycle, where you have the hot water going to a boiler, and inside the boiler there is the working fluid that's going through a Rankine cycle. That working fluid doesn't have to be steam, it can be anything if you want, and he's basically going through his boiler, turbine, his condenser, and then his pump, and on and on and on. And he's being heated in his boiler, which is really a big heat exchanger, by that brine. by that hot salty water that you are getting it from the from the aquifer, right? So that's what they call geopressurized. Okay, and this slide. He's talking about why we should bring back the water in, right? Because in order to prolong the lifetime of the source, you cannot just deplete the water. Okay, very good. And he's saying that the water takes forever to fill that aquifer, right? So that's why you cannot just like take the water and throw it in the river. You have to bring it back. And this is the place where he's talking about the how there is a life cycle. For that water to get hot, it takes a lot of a lot of days, a lot of years, 30 years. So in order basically to keep that place hot, we need to uh, use it carefully, and after the end life of the cycle, you basically the end life of the equipment, you will just basically move it to another place so that it can get hot again, maybe after another 50 years or something. All right. So now let's look up to the example in the book and how we can solve problems related to geothermal energy. So again, the hot source that is sending that water for us in hydrothermal system would be either coming on this side, that's liquid dominated, or coming on this side, and that is vapor dominated. So you would say a vapor dominated geothermal system. So you know that you are on this side, you are getting steam out of it. Alright? So that steam may have a lot or some particles in it, from the ground. So you need still a separator. It's not ready to go to the turbine yet. So what that separator do for you? If you look over here, he's saying if I'm getting at P1, I need to send it to a separator, which is a pressure drop, basically. As far as I'm concerned, that separator will end up causing pressure drop, and so you will end up dropping from the reservoir pressure, which is 3 megapascal, to the turbine pressure, which is 0.5 megapascal. So that process from 1 to 2 to 3, this is constant. What do you think? From 1, 2, and 3, this will be constant H. It's throttling process. So the H1 that you will get it from 3 megapascal, and this is Hg. So you open the steam table at 3 megapascal and you get Hg. The same H is gonna be H3. Okay, and once you know the pressure of the turbine, you said 0.5 megapascal turbine. Okay, and I know it's H, then I can get its entropy, right? I can get S3, and we know the deal. We did this before. Once you know the entropy at 3, first you say isentropic expansion, and you would say the entropy at 4s is the same as entropy at 3. And what do you do with the entropy over here? You got yourself S4s. What is that? That's the pressure of condenser. That will be given to you too. So it will tell you the turbine is running at 0.5 megapascal and the condenser is running at 15 kilopascal. Okay, so you got the entropy over here, and you say isentropic expansion, therefore I know the entropy over here. If you have S4s, this will allow you to get the quality, right? Quality at X4s. How you'd say the quality here is S4s minus SF divided by SFG, which is SG minus SF. Everything is done at 15 kilopascal. So knowing the entropy over here, the entropy over there, that basically the difference between them is called SFG, and basically the quality is this difference, S4s minus SF, divided by the SFG. You got yourself the quality. Why do you want the quality? Because you want the enthalpy here, right? You want H4S. Why do I need H4S? Well, that's how we can get the work of the turbine, and usually in a problem like this, he would say, well, if I want 100 megawatt, how much m dot do I need to pull, for example? So how are you gonna do this? Well, you're gonna say the power of the turbine is gonna be m dot time the delta H's, right? So let me pause here for a minute. Alright. So we were saying in order to come up with the m dot, for example, you would say that the power that he want, and he said he want 10 megawatt extracted. So to generate 10 megawatt, how are you gonna get this? Well, it's m dot time the delta H time a bunch of efficiency, right? The isentropic efficiency of the turbine and the generator efficiency. Very good. So I need the H's, and that's why we want this H. And in order to come this H, we need the quality. So that's what we are doing. So using the entropy, same as S3, therefore you will be able to say, I got myself the quality over here, and once I have the quality over here, I can get the H over here. So the H over here is going to be the HF plus the quality X4S multiplied by HFG, which is HG minus HF, right? Very good. So I got myself now H4S, and so I got work ideal now because it's H3 minus H4S. I got the work ideal, and so I'm ready now to come with the m dot, because I could say that the 10 megawatt is m dot time H3 minus H4S, not H4, H4S time the isentropic efficiency time the generator. Okay, or the old-fashioned way basically say, well, no, let's get H4 first, not H4S. How do you get H4? Well, the isentropic efficiency, the 82% is what? Is work actual divided by work ideal. So H3 minus H4 divided by H3 minus H4S. You got H3 and H4S, and you got the 82%. You can get H4. And so now, if you have H3 and H4, that's work actual. So now the m dot time work actual multiplied by only the generator efficiency is the 10 megawatt. Okay. Either way, you got yourself m dot. There's a benefit of getting H4 and not just doing H4S in case he is asking about something about the condenser. You know, how much cooling does a cooling tower need, or how much m dot water need to go into the cooling tower to cool the condenser. So in in this scenario, you would need H4. Okay. So he over here he said if re-injection occur at the cooling tower, analyze the system performance, thermal efficiency, and heat rate. And so what is the flow rate of the steam required for power generation? We got the m dot steam. So now the re-injection that happened at the tower. So this is the example is coming from the book, right? And you can see how what's going on. He finished the turbine, sending the steam at 4 into the condenser. The condenser is supposed to condense that steam all the way to 5, H5. And once he's at H5, he need to pump it up to what? To the ground, right? Because the ground, if he's gonna send it back to the ground is sitting at 3 megapascal, right? So he need to send it up to 3 megapascal so that he can send it back again to his boiler. See that place underground here is the is the boiler, right? So in the book it's confusing because you would think he's actually cooling the water first, then after it's cold, then he send it into the injection well. So a better choice would be, no, let's just inject it directly after pumping it. Why would we have to cool it? Let's send it hot, right? It's kind of like really saving the heat source over here, and also we don't get any benefit by heating the air, right? And we don't need to heat all that water. But anyway, you will see another example in another book where they actually inject directly after the pump. Okay, But the reason why it's not a big deal is that you will find out that the m dot through the cooling tower is really very big compared to that m dot. So that extra m dot either going here or going through the cooling tower and coming back is not that big difference. Okay? And if you're wondering why does it take a lot of m dot going through the cooling tower, you will see that by applying the first law of thermodynamics. Well, that small m dot that's going through the turbine need to drop from H4 to H5. That is a big delta H between H4 and H5 to turn that steam, mainly steam. When it's 4, it's not all steam, it's part water. But to turn all that H4 to H5, that's big delta H, and you are doing it by what? By a very small drop in the water temperature. So the water leave at 6, leave the pump at 6 and go to the cooling tower and come to 7. So the water going from 7 to 5, that's not big delta H. It's coming into the condenser at 7 and it's leaving at 5. That small delta H are supposed to cool all that steam from 4 to 5, and that's why it takes a lot of m dot compared to this m dot. Okay, so here is the example with the numbers. Alright, going from 3 megapascal to 0.5, and this is, I'm trying to explain here exactly what is going into the cooling tower. Okay, so the cooling tower, there is two modes for the cooling tower. He can be dry cooling tower or he can be wet cooling tower. So what is a dry cooling tower? A dry cooling tower is your car radiator. That's a dry cooling tower. The coolant, which is in this case water, coming here at 6, go into a bunch of pipes and being cooled by air from the outside, pulled by fans, right? The big cooling tower that you see in nuclear power plant, that can be without any fan. That can be natural convection. Just the fact that the chimney or the stack is so high, he will pull the air by just buoyancy force. But short ones, like the one you see them in Tulsa, in Jenks power plant, for example, or bunch of power plant we have all over the town, those are short. They don't have enough buoyancy force to drive that flow, so they will be aided by fans, either at the exit or at the inlet. They put them from the side and they let the air go in and basically cool the water. So in the TS, this is the TS diagram. I'm expanding this point because the book didn't really make it big enough. So what happened after 5? After the water condensed from 4 to 5, it's pumped up to 6, 5 to 6, go up like this, and then the water coming at 6, it will get cooled at constant pressure. Constant pressure, well, there's a little bit of pressure drop in the pipe, right? But assume constant pressure from 6 to 7. So how low 7 can be? How low or how effective the cooling tower can do the job? If you come at 6, you can drop to the best thing ever that could happen to you is that you drop to what do you think? The air temperature, the air that's cooling you, right? So specifically the dry pulp temperature of the air. Okay, people who took thermal fluid design 3524, remember there's the dry bulb temperature and the wet bulb temperature, and the wet bulb temperature is colder because the evaporation of the water. So if we're gonna do a dry cooling tower, no evaporation, water going into a pipe cooled by air, then that 7, the water in the pipe, can get best ever can go to the dry bulb temperature. But if we do a wet bulb, a wet cooling tower, that's basically a cooling tower where you spray water and the water is cooled by the air, but while the water is being cooled by the air in a spray shower fashion, the water evaporates. And that, well, that have two things. One, the water will actually end up going to evaporate. So so when the water evaporate, you lose some of the water. That is the bad news. So the wet cooling tower will basically have water vapor leaving, right? And the a funny story is that I have a friend that working for the power plants over here, and her sister showed her took a picture one time of the cooling tower. You know, south of Tulsa, there is like a lot of cooling tower on the river, and they were like sending all those clouds of water vapor because it's a wet cooling tower, so the water is evaporating, and in a cold winter day, those become like big plumes of clouds basically coming out. And her sister told her, "Look at the pollution that you guys are doing to us, all that smoke coming out." And of course, it's funny because my friend know that no, it's not uh, any pollution. This is just water vapor. We are making clouds basically, right? It's funny, right? So so anyway, so if you have wet cooling tower, you can drop that 7, that state 7 to the wet bulb temperature, okay, which is usually colder than the dry bulb temperature as long as the air is not 100% saturated. If the air is not 100% saturated, then you can drop his temperature from the dry bulb temperature to the wet bulb temperature. Either way, you get H7 which is reduced, right? And then this H7 is sprayed back again into the condenser. So this is called direct contact condenser. So that direct contact condenser is again as if he is really a wet cooling tower. So you spray the water in the steam and the steam condense on it, and he go from 4 to 5. And you can see what I was talking about before. The steam is coming from H4 all the way to H5, big delta H. And the water that we are spraying on him to cool him, to, to take that latent heat, is now gonna do what? Is gonna be sprayed at 7, and it's supposed to rise to 5. So the difference between 7 to 5 is not that big. Huh? H7 minus H5, sorry, H5 minus H7. H5 minus H7 is not that big compared to H4 and H5. So the first law tell you that m dot steam time H4 minus H5 is going to be equal to m dot cooling tower time H5 minus H7, right? Qn equal Q out. And so that's why it takes a lot of water to cool that m dot steam. Alright? So as always, what is the thermal efficiency of the cycle? Work net, right? And work net is work turbine minus work pump, and you can see he's neglecting work pump. He's neglecting work pump to the extent that he doesn't even show it on the TS diagram, but it should be something like this. Once you finish 5, you go up to 6, right? And so that's work net. Ouch. And what is Q added? Where is the boiler? This is the boiler, the ground. We send stuff to H7 in that example. In another example, you will see that he will send it at H6, but again the difference is not that big, and he bring it back at H1. So Q added is H1 minus H7. Alright? And so if you read the number in the book, you will see exactly what we said, how he's saying the throttling part. See, I would think this is the hardest part in the problem. The fact that you realize that H1 is the same as H3. And once you have H3 and the pressure, you'll be able to get the entropy. That is the key to this problem. You get the entropy, then you can go down there and get the entropy. Alright? That's what he's saying here. Look at that. S4S equal S3. And he's getting the quality, and from the quality he's getting the entropy, and work ideal, and then work actual multiplied by the I think he didn't multiply by the eta electric actually, which is supposed to be 90%, right? Was it 90%? Yeah, generator is 90%, and the isentropic efficiency is 82. So notice that if you use this example, this is supposed to be 0.9. Okay? So, or actually no, he is saying work actual is work eta. It's not eta electric, it's eta isentropic. This should have been eta isentropic, work time, work ideal. Then that's fine. And then then he is adding ETA electric over here at the end. Okay, one more thing. What is the heat rate? What is the heat rate? So the heat rate, what is the thermal efficiency first? Thermal efficiency is work net over Q added. The heat rate is the opposite. The heat rate is the heat added divided by work net. So you should think of it as 1 over the efficiency. Fine, 1 over the efficiency. So if the thermal efficiency is 0.5 or 0.46 or something, 0.4, then the heat rate will be 1 over 0.4. That's okay. But remember, the efficiency is, what unit do we have for the efficiency? Dimensionless. The efficiency is dimensionless, right? When you say work net over Q added, both of them should be in kilojoule per kilogram, or both of them should be in megawatt over megawatt. So the efficiency is dimensionless, but the heat rate has to have units, specific units. The Q is in BTU and the work is in kilowatt hour. So kilowatt hour, that's kind of joule, and BTU, this is kind of joule. Yes, it's joule over joule. It's still dimensionless. I mean, because it's 1 over the efficiency, but he specifically wants those units, BTU per kilowatt hour. And why is that? Why they care about BTU per kilowatt hour? And so, by the way, what is the result of all this thing? That conversion between BTU and kilowatt hour will result in 3412 over ETA thermal. So basically the heat rate is 3412 divided by the ETA thermal. Okay? And what's ETA thermal? Work net over Q added, dimensionless. So now why do they care about BTU per kilowatt hour? Because if you are operating a power plant, you charge your customer for kilowatt hour. You sell to Tulsa, and you know that you are selling to them for 11 cents per kilowatt hour. So the kilowatt hour that you produce out of your generator is your revenue, right? That's how money you can collect at the end. And you buy natural gas from the natural gas company, and your bill come from the natural gas company. As a power plant, you pay per BTU. So they charge you per BTU. I mean, they are sending flow rate, right? They are sending flow rate of gas, natural gas. But they, as if all of you, you know, if you have a home, you will look at the gas bill, and it's basically for BTU. So they figure, well, how much is the energy that we are sending in our flow rate. So although they measure the flow rate they are sending to you, but they would say, we are sending them this much flow rate, therefore this is equivalent to this much this much BTU. So as a result, this number, BTU per kilowatt hour, tell the operator of a power plant, is he making money or losing money? Because it's basically how much he pay and how much he is being paid. Okay, so they want this number to be less than 10,000, of course. Well, over here it's 22,000. That is like really horrible. But this is a geothermal power plant, right? So the BTU is really for free. So again, all renewable energy source, we shouldn't frown on their thermal efficiency or their heat rate. Why? Because we are not paying for the fuel. What really matter at the end of the day is the cost of the kilowatt hour. And the cost of the kilowatt hour is not the fuel, is not the Q added. The cost is the initial cost and the operating cost. How much dollar did we put in building this power plant? How long it will survive? How many kilowatt hour will it produce during all its lifespan? And therefore then we can figure out how much each kilowatt hour is costing us, and whether then at the end of the day we are making profit of it or we are selling at a loss. Right? Very good. So here is bunch of examples on a power plant that's geothermal power plant that already exists all over the world. Right? And historically, I think the first one ever was like in Italy. Right? The first one that they ever get power out of it was in Italy. So now let's look at if we are not lucky and get steam directly out of the plant, what will happen?